Okay, on last Thursday, we spent some time to derive two equivalent circuits, starting from the voltage equations and flux equations. So we make use of some features from the LAD, LAQ per unit system. Because based on the LAD, LAQ per unit system, any mutual inductance involve stator winding in D axis will be LAD. In Q axis will be LAQ. So that's why we will see many LAD and also LAQ. So that largely simplify the equivalent circuits. So in the original circuits, when we present that the like 3-winding transformer type of equivalent circuits, those mutual inductances presented with different windings. But right now, they share the same per unit value, so they can be presented at the same branch, which is this LAD in D axis and LQ in the Q axis. So that can largely simplify the equivalent circuits. So at the end of last lecture, we start from the voltage and flux equation. We try to put all the currents which are flowing through the LED into the same term. So that can be modeled by the same branch in the circuit. Similarly, we'll put everything involving the LAQ in the same branch. So we color that branch, so we can add one branch in the equivalent circuit. We just gradually move forward. Eventually, we derive these circuits in D axis and the other circuit in the Q axis. So which gave us accurate presentation about the voltage and flux equations. Okay, so this will be our starting point for the generator modeling. So right now we have even simpler model. Just only give out two circuits, and also it's present how the voltage is induced proportional to the speed of the rotor. Okay, so this is considered the speed voltage of the generator, and another source which will be the DC source generating the magnetic field with the field winding, but that is not the major source of this generator. Yeah.
So if we come to the ground rotor for that DC source for the G and Q, that's as it will be have also on that circuit. So I definitely for the DC source. So if just come to
there's only one DC source, which is the field winding. There's no other DC source at all. Right, because that's only the input of the entire model, entire system. For round rotor generator, we can add a second branch, just to make each circuit has two branches representing the rotor. So for symmetry, if you add a third one, that's fine. You can also add a third one for D axis. So you can have two damper winding D axis and three damper winding Q axis. So plus the field winding D axis, you have three branches in each circuit. That's also fine. And the good thing with such equivalent circuits is it put one circuit connecting both the stator side and also the rotor side. So which is similar to the equivalent circuit or for the generator or transformer you have learned for the steady state analysis. So in the generator equivalent circuit, you have internal source, which behave like a EMF, electromotive force, and connected to a reactance and resistance into the external system. So we're going to show that equivalent circuit came from those two circuits by simplifying some parameters. And for transformer, also it's not convenient to have two circuits, one for primary winding, the other for secondary winding, but which are isolated, right? So you want to connect the two winding into the same circuit. So having just single circuit to do the study is always more convenient. So on these slides, we have to change the naming convention. So from now, we don't want to call them like a LF, RF, or LED because they are meaningful in the original circuit. But in this equivalent circuit, we only want to give each indictance of any branch just a single name, single notation. For instance, this indictance is on this branch related to damper winding DSCs. We just call it L1D. So D means damper winding. Sorry, D means DSCs, and 1 means the first damper winding. Okay, so R1D means the first, the resistance of first damper winding DSCs. But from this equation, the meaning is, so this value is exactly RD, exactly the resistance in the damper winding. But L1D is not LD. L1D, although it's related to damper winding, but it's not a self-indulgence in damper winding. It's actually self-indulgence in damper winding, and minus, this is MR. What is this MR? MR is like a mutual indulgence of a stator ending, but not a couple. Anyway, will be here, right? But from here, we just assume MR to be same as LAD. So L1D is actually the LD, the difference of LD compared to LAD, compared to mutual indulgence. And we just call the capital F as EFD, which means field voltage and field resistance. And LFD is not the field winding indulgence. Actually, the field winding indulgence minus the mutual indulgence. So we're going to utilize those orange notations in the equations, and later we may also utilize their original indulgence or resistance notations for some derivation. But from now, we can use both. So this is just the last slide I presented, showing this equivalent circuit so far is the almost like most accurate circuit you can use in any of the stability study. Okay, so if you give every indulgence or resistance a value, so this circuit will have 3 branches for DSCs for the rotor and 3 branches for the QSCs for the rotor. All right, so now we use those 2 equivalent circuits with new notations for the indulgence or resistance of each branch. We also need to somehow change the voltage equation and flux equation. We are going to rewrite those equations as the following equations. So those equations are exactly equivalent to the original equation. We just change the namings of those indulgences or resistance. For instance, this equation also, okay, so we ignore the zero sequence flux linkage and voltage because for most of the balance condition, the psi 0 and E0 will be 0. So we only focus on the phi voltage equation and the phi flux linkage equation. So for instance, we pick this, the second equation about the psi D. So that one will be equal to LL plus LAD. That is the total indulgence multiplied by ID. Okay. So LL plus LAD will be LD. So that will be the first term. So the next term, LAD multiplied by IF, will be LAD multiplied by IFD. Your IFD simply does IF, the same thing, same current. Then the last term is LAD multiplied by ID. ID is from this figure, it is actually ID, I capital B become I1D. So it will give you this last term. Okay, so you simply just write each equation down using the old notations, and by using those figures, you translate into the new notations. So they will become those 2 sets of equations. And those parameters will be the typical parameter you can see from many generator models, from some software tools from the commercial software vendor. On Quinter's book, there's one example, 3.1. So you can utilize this example to do some calculations regarding the parameters of the model and also change the value from the original value to per unit value. So let's consider a 555 MV. This is like the power base. This is like power base. And 24 kV. 24 kV typically means line-to-line voltage. Okay. And in RMS value, the root mean square value. And power factor is 0.9 and 60 Hertz, three phases and 2 poles. 2 poles means this is round rotor generator. So you can imagine there's a symmetry between the D and the Q axis. Even that may not be perfect, but it will be, you'll have very close values between the D and the Q axis. So first they give you IOA. IOA is actually the self-inductance of the winding A. So this is not a good parameter because they theta dependent. It changes with a cosine function. Also give you IOAB, right? We know IOAB will be negative value because the winding A and the winding B is separated by more than 90 degrees. Okay, so no matter how you project those two quantities, in which direction, they're always opposite to each other. So they will be negative. Also, it's a cosine function of 2 theta. So then the IOAF is actually the mutual inductance between the winding A and the field winding. So this is also a cosine function. So IOA and IOAB both have the period of 180 degrees, but IOAF has 360 degrees. And LF is a self-inductance on the rotor. So this one doesn't depend on theta, right? For any quantity on the rotor, that doesn't depend on theta. And it also assumes the resistance in the stator winding and in the field winding have those values. So we need to calculate IOD and IOQ in the unit of Henry. So if we know the leakage inductance is this value, so we want to determine LAD and LAQ. LAD is equal to LD minus LL. LAQ is LQ minus LL, okay? Then we can use the machine rated value as the base value for stator quantities and to determine per unit value. And also we need to consider the LAD based reciprocal per unit system. So here we just simply assume LAD is equal to MF equal to MR in per unit. So we're going to calculate the following parameters. So first we just put the LA in this line and compare to the formula. We know the constant part is LS, which is self-inductance of stator winding. LM is actually the magnitude of the oscillating part. So corresponding to that equation, we can just color them just to identify those items. So IOEB has the constant part, which is negative MS. Okay. So then based on the definition of IOD, we can quickly calculate IOD will be 4.981225 millihenry. And IOQ is not equal, but it's very close because this is round rotor generator. It's pretty close to IOD. Then we can calculate LAD and LAQ. We just do that, do the subtraction. So we'll have LAD and LAQ. So they're all in the physical unit, millihenry. Okay, next we want to calculate other parameters. Then we calculate the per unit value. So we need 3 bases. We need for stator winding, we need a power 3-phase power base, and we need a voltage base, peak instantaneous voltage base, and the current base. But we so far only have the 3-phase power base, which is 555 MVA, but we do know the 24 kV is actually the line-to-line voltage in the RMS value. So we divide 24 by √3. So this one will give you the voltage of each phase. And we also know the electric speed base will be 377 radian per second for a 60 Hz system. Okay, next we can calculate the voltage base, which is for the peak value of instantaneous voltage which will be just the RMS value multiplied by √2. So it will give you this one. So this will be the voltage base for each phase. So for the current, we can calculate the RMS value for current. So we simply just let the three-phase power divided by 3, then divided by the RMS value of voltage. So we'll have, this is the current for RMS value, and which means the instantaneous current, peak current, will be the RMS value multiplied by √2. So it will give you this value. So now we have all the three bases. So we can calculate the other bases. The impedance base will be the instantaneous voltage base divided by instantaneous current base. Inductance base will be the impedance base divided by the omega base. Okay, so next, so those are for the stator quantities. For rotors, first we need to calculate the field winding current base. The field winding current base is equal to the stator current base multiplied by a factor. The factor is LAD divided by MF. So that factor is just try to make the mutual inductance in the field winding is equal to the mutual inductance with stator in terms of per unit. So we actually proved this equation from a previous lecture, right? So if this equation holds and we use this current base, we can make sure first the power base of the stator rotor have to be same. Then we can make sure the mutual inductance in the will become LAD in per unit. So the voltage base in field winding will be the same three-phase power base divided by the current base. So you can just directly get the impedance base for field winding. So the inductance base will be impedance divided by omega base. So this MF base will, then you just follow the formulas we learned from a previous lecture. So per unit value, those will be the per unit value. We use the actual values from previous slide and to be divided by the base values, we'll have those per unit value. So IOAD, IOAQ are very close because this is round rotor generator. Those are the per unit values. We'll come back to this example later when we'll keep using the same generator for any derivation or a simplification of the generator model. Okay, we'll utilize the values, like some value is much bigger than some other value. We can somehow ignore the smaller one to make the model even more simpler. But we will come back later. Okay, next I want to talk about the steady state analysis. So if you want to do steady state analysis, and we really don't need to have those two very detailed circuits, we can largely simplify the two circuits. You can imagine our final goal is to have a single circuit, which is internal voltage connected to a reactance and resistance and to the external system, right? That's the equivalent circuit you have been familiar with for steady state analysis. But right now, we need to do that, prove that circuit is good, starting from those two detailed circuits. So after we change the notations of those the inductances and the resistances, we'll have a new set of equations. So those equations are same as the voltage flux equation before. We just change the notation, right, to match those two circuits. Okay, so we start from this set of equation and those two equivalent circuits. Let's see how we can simplify some parameters under the steady state condition. So first thing we can know is for steady state condition, all derivatives are zero because the system is under steady state. Steady state, which means at equilibrium. So we can ignore any variation. Because variation will in this set of equation will indicate some flux or current or voltage will change with time. But if you consider steady state condition, any items with P is actually the differential operator. Because differential operator itself becomes zero. Anything with P will become zero. We just simply just cross off everything here. Let me do it on the slides. Okay, so doesn't allow me to. It's weird. Okay, it doesn't work on my computer. So okay. So any atom with P will be zero. We just get rid of those atoms. So the remaining part will be on the steady state condition. And there's also something else we can further simplify. I will talk about that. And also we know the speed doesn't change. It will be a constant 60 Hertz. So P omega will be zero. P omega zero, which means omega r in per unit will be 1. So L will be equal to X. Because X is equal to omega multiplied by L. So inductance is equal to the reactance in per unit values. So P psi at D is zero, which means this atom is crossed off. So immediately we know the field voltage is actually the product of the RFD and IFD. So which means on this circuit, which is equivalent to do a short circuit connection between those two terminals. So we will get rid of the impact of this branch from the first circuit. Next, for the psi 1D, which is a flux linkage in the damper winding, first damper winding D axis. So this one, it doesn't change. So the derivative will be zero, and which means on this circuit, so this voltage between the two terminal will be zero. So if this voltage is zero, there's no induced current. The damper current in the DSA will be zero. I1D will be zero. Because this damper winding current comes from the variation of this flux based on the function of the damper winding. So if under steady state condition, there's no variation of the oscillation of the rotor. So there's no damper winding current induced. So damper winding current is zero. Similarly, in the Q axis, this one will be zero, which is equivalent to open the circuit of this at this point, at 2 points in the D and Q axis to make the current zero. So immediately when we come to the equation, psi D, okay. So get rid of the last item. This current will be 0. And also this is 0, this is 0, this is 0, this is 0. So we cross off all the items in, which carry the damper winding currents in either D or Q axis. So that make the flux linkage equation for the stator flux in D axis, Q axis be much simpler. So next we assume the psi D doesn't change. Psi D is actually the stator flux linkage. So if psi D doesn't change, which is equivalent to do a short circuit connection between those two terminals. So finally, only there's a two item influence the terminal voltage. One is the current flowing through this resistance, and the other will be proportional to the flux linkage in the Q axis. And this voltage is caused by this branch. Because this branch, this orange branch, generate the flux linkage of in Q axis. And this flux linkage multiplied by omega r will become the source in the stator winding of the D axis. Similarly, for the Q axis, those two terminals also have short circuit connection. And that make the voltage in the Q axis for the terminal only depend on the voltage drop on the resistance and also a source proportional to the flux linkage in D axis. So this one will come from this green branch. Okay. So then we can do some, we just get rid of any item which has become 0. So we will have a new set of equation. And there's some equation which is doesn't have, let's start from 0 on the right-hand side. We already just simply get rid of, oh yeah, this one also need to be get rid of. So that equation is removed. So this one also 0, this is all 0. Yeah. That's pretty much everything. Okay. So now we only have 3 voltage equations and 3 flux linkage equations. And both equations become algebra equations. So they're not differential equation anymore. And damper winding currents are 0 under steady state condition. So now we have simpler circuits, but it's still presented as separate D axis circuit and Q axis circuit. So to summarize what we changed on the original two circuits, first we add a line to short circuit connection between the terminal for the field winding branch. Then we open the circuit, open the branch in both damper winding. Then we do a 2 short circuit connection on the both stator branches. So, but we don't want to always draw this circuit in our analysis. We want to combine anything here into maybe a single circuit. So our next goal is to derive a single equivalent circuit for both D and Q axis. Okay, so now we introduce the terminal current. Terminal current is defined to be the current, instantaneous current in the D axis plus J multiplying the current in the Q axis. So here IT tilde means it's a phasor. Okay, so it has component in D axis and also component in the Q axis. So we use one complex number to indicate the total current, considering both D and Q components. Similarly, we can define the voltage, terminal voltage phasor, which is ET tilde, which has the real part, which is the lowercase ed, and imaginary part, lowercase eq. Okay, so based on the state equation we have, we just plug in the equations on the ED and EQ here, so we can have this expression. So for this expression, we want to utilize the definition of IT. We want to, because on the right-hand side of the equation, we have IQ, ID, IQ. We have many DOQ ICs components for the current. So we want to find one ID and one IQ to combine them to become IT. Okay. So immediately we can do that for resistance. So for the resistance, we have RA times ID. We have RA times IQ. So they both have negative sign. So we can immediately bring those two blue items to the front. So this will be the RA multiplied by the IT. So we construct item in the parentheses as IT tilde. Okay. Then for the ISQ is the readiness multiplied by IQ. We need to create one item which is like ISQ multiplied by ID, but there's no such item at all, right? There could be ISD multiplied by ID, but which is not ISQ multiplied by ID. So we can create one item which is ISQ multiplied by ID. And for this item, if you compare to the blue items on the resistance, we know for the IQ component it comes with an imaginary unit J. So we also so whenever we see IQ, we give it imaginary unit. So which means we also add another imaginary unit, right? Negative J multiplied J, that will be 1. So this one, the ISQ IQ will become negative J ISQ times J IQ. And the next one will create another item which is same as J ISQ, but we multiply by ID. But this is newly created item. We have to add this opposite to cancel it. So those two just cancel each other. And for anything else, we just move here. All right. So now we can merge the first two orange items into something like one reactance multiplied by the current phasor. But for anything else, for the last three items, they have a common thing, which is they are all in the same direction because they are all purely imaginary, which means they are all pointing to the same direction. So we just simply define the summation of the last three items as some internal voltage. So that is the internal voltage or the EMF of the generator model. We simply just define everything here as internal voltage, and that one is in the is purely imaginary. Purely imaginary means it's in the Q axis. So that's why we define it as EQ. So now the voltage equation becomes just single equation. So terminal voltage is equal to a negative. There's a resistance plus some reactance. So this can be considered as, this one can be considered as like internal impedance multiplied by terminal current, then plus internal voltage. So if we realize this equation by this circuit, so it will be exactly this circuit. So I have internal voltage, we call it EQ, because it's always in the Q axis with certain angle. And this will be the internal EMF. It generates voltage, and there will be a current coming from this source, first going through the RA. RA is actually the stator resistance, then go through the reactance in the Q axis, and then go to the external system. So the voltage and the current as external system will be ET and IT. Tilde means it can be a phasor. Without tilde means it's just a scalar value, but you have to add certain angle. Okay, so this is the equivalent circuit we have been familiar with in the static analysis. So this slide just goes through this process to prove this equivalent circuit. This is not a proximate circuit, right? For the static condition, this is accurate circuit. There's no approximation so far. Everything is accurate, but the condition is it's a steady state analysis, right? All the derivative are 0. Any question?
Why R is 1?
Omega R is per unit. Per unit means it's same as the synchronous frequency. Per unit, omega R is
Okay. It's 1, not 0.9. Because it's just a constant, not exact.
because typically, yeah, you raise a good question. So you can have a power system operating like 55 hertz, right? If that's the case, it will be not 1, but for BPS or BES, based on NERSC standard, that frequency should be very close to 60. And if you consider automatic generation control, that frequency need to almost always go back to 60 hertz for any static condition.
I mean, is that like a pro? I mean, not from this condition, that so it may not accurate model, right? Maybe.
Yeah, mathematically speaking, yeah, you're right. So it's not accurate. But if I'm saying this is static analysis and omega R is 1, yeah, that's right. But if you make omega R be 0.9, it doesn't mean this circuit is not correct. It will still have circuit. Yeah, right. But parameter will be different. First, X will not be L. Those will be different. So if you took a 421 or any other power system analysis for static condition, so you might have learned this equivalent circuit. So in that equivalent circuit, usually for the radiance, we use a notation which is XS. We call it a steady state radiance. So from this circuit now, you know that radiance has to be ISQ. So it's not SD, it has to be ISQ. For round rotor generator, maybe ISQ, SD will be very close, so you can use any one. If you really want to dig into why this one is not SD, you can go through the same approach. But in my approach, I try to create one atom, which is like terminal current multiplying some radiance. So here I assume that radiance is ISQ. You can assume that one to be SD. Then you will see what will be the last 3 atom. So you will find out the last 3 atom will not be pointing to the same direction. So that can make you still can create such circuit, but that internal voltage will be pointing to a direction not in the Q axis. Will be some direction separated by a certain angle. So that make a calculation be more complex, but it's more convenient to use ISQ at a similar radiance. Okay. Yeah, for round rotor generator, if you ignore saliency, SD, ISQ, SS, you can use either one as a singular radiance. And also for round rotor generator, you can also ignore this term, this atom. So this atom is proportional to the difference between the D and the Q axis inductances. And if this one is 0, so EQ, this internal voltage is proportional to field voltage. This makes a lot of sense. So you have a internal voltage, and that voltage is proportional to the field voltage, or field current. So if you increase field current, you are going to increase this voltage. So for the exciter control, to change the terminal voltage, that is try to utilize a feedback control system based on the gap between the terminal voltage from some reference value. You can influence the field current. By changing the field current, you change the EQ. By changing EQ, you can change the ET. So finally, you can stabilize the terminal voltage at any reference value. So that's the idea of exciter control. So we'll have the whole section about voltage control, so we can talk more about that.
Why EQ is exactly related to XD?
So why, from where you see it's
That's the question. Why EQ is partially related to XQ?
so why is it not positively related? So if you assume negative sign, where does that negative sign come from? So this EQ is just a magnitude of some phasor value. So that, which is like a voltage waveform. That waveform is proportional to the magnitude of a field current. So your question is,
Partially related to XD. The D reactance of DX.
I don't understand your question.
Why this is a vector this one.
That is from the Hopper proof, right? That is what that is called by mass.
In physical,
Why XD and XQ are equal?
Yeah, he was asking why there's a negative sign here, but I told him the negative sign came from all above. Yeah, you can think about why this is negative sign, not positive sign physically. Yeah, share with us in the next lecture, but that's not our focus. Okay, so we can calculate per unit values for steady state condition. We assume omega r to be 1 per unit, and compressed power is defined as the voltage phasor multiplied by conjugated value of a current phasor, right? Everybody familiar with this one? Okay, tilde here is just phasor in Quinter's book or in this course. So ET will have real part, imaginary part coming from the D axis and Q axis. Current will also come from D and Q, but this negative sign is because we have conjugate. We take conjugated value of the current. And you just do the calculation to get this step, and the real part will become active power, and imaginary power will become reactive power. And from previous slides, we know ED is equal to 1 voltage proportional to the flux linkage in the Q and also the voltage drop on the resistance. Similarly, for EQ, well, they also depend on the flux linkage from D and also the voltage drop on the resistance. Okay, immediately we know the IT power, we call it PT. T that stands for terminal of the generator. So it will be the real part from the compressed power. So you can plug in the ED and EQ based on the 2 voltage equation. So you have this one. So you can and compare to this one. So the second item means the power consumed by the resistance of the stator. And the first item really means the electric power generated by the source. So the PE is actually electric power come from this EMF. Then some power will be lost due to the resistance. And terminal, you only receive PT. Also, we know the imaginary part of compressed power will be QT, which is the reactive power. Okay. So if you took my 421, I actually explained IT power is the inner product of the voltage and current vector, because this expression is the definition of inner product. And QT is the vector product of a voltage and current vector. So this is exactly the definition of vector product. So if you have a voltage vector with ED, EQ as component, you have another vector as ID, IQ as component. The 2 vectors the wedge product, which is basically take value of cross product, will be equal to QT. So the meaning of QT is really just the wedge product of voltage and current vector. Okay, so next one, the electric torque will be electric power divided by the speed. Another thing we need to talk about will be the angle. So the EQ will have angle delta I. So why we call it delta I and not delta? Because it is not rotor angle. It is related to rotor angle. It is like some internal angle with this EMF, electromotive force. The actual rotor angle is really this angle. We have to define some reference. So if we use terminal as a reference, if we assume the terminal is connected to a very large system, that large system doesn't oscillate, or that large system has constant angle. So we can use this angle of the ET as a reference. So here we assume that to be 0, but if it's not 0, that angle will be a reference. So that angle plus the angle of delta I will be really the rotor angle. Okay, remember how we define the rotor angle. The rotor angle defined to be the position of the rotor relative to a common reference. So if you define the external system to be the common reference, so your delta need to be equal to the terminal angle plus that delta I. But definitely, if you define this internal source itself as reference, the rotor angle will be delta I. Right? All right, so we can draw phasor diagram based on any equations about the phasor quantities. So I assume everyone has been very familiar with how to come up with this phasor diagram. To draw the phasor diagram, we need to have phasor or vector representing each item in the equation, which has complex value with real and imaginary part. First, you need to define a reference. So if we assume ET has angle is 0, so we draw the reference, which is x-axis as 0 with 0 angle. So this will be ET. Okay, so start from ET. And so there will go through a number of voltage drop. Eventually, we'll come to this EQ. So the first voltage definitely will first need to draw this current. We assume power factor phi. So for this case, we assume the external system will have lagging power factor, which means the current is lagging the voltage. Because this ET is going to the load, current also going to the load. If this current is lagging the voltage, phi will be negative. Or in other words, if you define phi to be the angle by which current lags the voltage, the phi will be positive. So anyway, so current will be behind voltage by angle phi. So next, we have to draw the voltage drop on the resistance and on the reactance. So for the resistance, that will be this current multiplied by that resistance. So we need to draw a very little arrow, right, in parallel with this current. Then we draw another vector orthogonal to current because the reactance is imaginary. Okay, so we draw another vector orthogonal to current by turning the direction of current counterclockwise by 90 degrees. So the total will be the voltage drop on this entire branch. Then that will be the Q axis. So later in the Q, we assume the Q axis to be the imaginary axis, and D axis, which is lagging Q by 90 degrees, will be the real axis. So if we use complex number. All right. So next question will be how to solve this delta I. So if we solve delta I and we add the angle of the terminal, we'll actually know the rotor angle. So this is very important to calculate this delta I. From the ECE 421, we already proved the equation to calculate delta I, but now we can just quickly do that. So here, first of all, the magnitude of current can be easily calculated by power divided by the voltage, and power factor can be calculated from the ID power and apparent power, then by calculate the R cosine, so we can get phi. So then we can use this formula to calculate delta I. So the idea to calculate delta I is actually we utilize this triangle. Okay, so this triangle. Because delta I is actually the tangent delta is actually equal to this part divided by that part. So we'll calculate this part by numerator in this formula, right? This part will be equal to this part, which is equal to SQ IT cosine phi. Then subtract this little item, which is RA IT sine phi, which is the numerator. Okay, divided by this H, okay, which is ET, then plus a little part, which is equal to RA IT cosine phi, then another little part, which is SQIT sine phi. Yeah, just spend some time, you can easily prove this formula is true. Okay. But keep in mind, this formula is only good for lagging power factor. If it's a leading power factor, which means the phi is negative, the current is a leading voltage, or the generator is operating as a load, the current is separate voltage by more than 90 degrees. So formula will still be like this one, but you can imagine somewhere we'll have a negative sign. Some positive sign become negative, some negative become positive. So in the homework, you're going to solve for some conditions with different power factors. So keep that in mind to make sure to draw the phasor diagram and check, decide which triangle you're going to utilize to calculate the tangent delta, and then you can check the formula to make sure all the signs are correct. Any question? All right, so there's only one thing which is not covered yet, which is about saturation. So far, we derived the two circuits which are accurate if the generator is not saturated. But saturation means when you increase the field current, eventually the flux linkage or the inductance will not be proportional to the current, will saturate, because the magnetic field is too much, will be it cannot increase anymore. Okay, so which means in the two equivalent circuits still have the good structure, but we need to assume those two inductances, LED, LEQ, will be changing with the field current, will be function of a current, field current. So how do we model the magnetic saturation? So we can make a number of assumptions to simplify the study, especially for stability. The leakage flux are not significantly affected by saturation of the air portion, which means if you have estimated the leakage inductance LL, you can just keep that constant, okay? And you only assume the LED and LEQ will be changed. LED, LEQ actually about self-mutual inductance in the involving the stator winding. So they will change their values when the field current is varying. The second is there's no magnetic coupling between D and Q axis. This is pretty aware. So the saturations on D and Q axis can be studied separately, which means you need to find the inductance without saturation in the D axis and another value for Q axis. So when you increase the field current, those two will change individually. Okay. They are both function of the field current. So the LED, LEQ are equal to the LADU or LAQU only if the field current is not high. So it's not saturated yet. Another assumption is the leakage fluxes do not contribute to the air saturation. So the saturation is determined only by the air gap flux linkage. So what does this one mean? Okay, it means the flux linkage in D and Q axis can be calculated by those two equations, and the total flux linkage in the air gap need to consider both psi D and psi Q. We can treat psi D and psi Q as two components in two directions, two orthogonal directions. So we can assume there's a total magnetic field, which can be characterized by psi AT, which stands for the air gap flux linkage. Tilde means it's actually a phasor. It has both the magnitude and also direction. The direction will depend on the values in the D axis and Q axis. So which one is bigger, how they change the value. So we can make the psi AD to be the real part and psi Q to be the imaginary part. And the psi AD, psi Q will be just the flux linkage in the D and Q axis by ignoring the leakage, or you just add the leakage part. So finally, we create this phasor to represent the total magnetic field of total flux linkage in the generator. So if we know the real part, imaginary part, you can definitely use this law to calculate the magnetic magnitude of the flux linkage. So our next goal is to find how this one change with the field current. Okay, another assumption is the saturation relationship for the air gap flux linkage versus the field current is hard to measure under loaded condition. So usually manufacturer just do the estimation for no load condition by assuming the terminal current to be 0, and which means they just only study the open circuit characteristic for the generator, but they just simply use this characteristic as the condition with load condition. So that's not accurate, but that's the best practice. Okay. For stability study, that's good enough. If you want to study how to design the generator and how to design protection, maybe you need to have better formula. But for this course, if we only are focused to study the stability of power system, this practice is really good enough. Okay, so which means when we calculate the flux, the air gap flux linkage, we can assume ID and IQ both be 0. So that largely simplify this equation. So eventually, air gap flux linkage is just proportional to the field current. And that coefficient will be LAD. So if LIFD increase and LAD, if LAD is saturated, the flux linkage will saturate. Okay, so now we can introduce two factors that just indicate the scale, how much the generator is saturated. So if that factor is 1, which means no saturation. Okay, if it's lower than 1, which means with saturation. So if we study ceiling pole rotor generators, the path for QSA flux is largely in air. So LAQ does not vary significantly with saturation, which means we can ignore the saturation in LAQ. So we can use constant as a LAQ for ceiling pole rotor generator. So such as the factor in QSA is always assumed to be 1. Okay, we only just consider saturation in the D axis. For round rotor generator, because it has a symmetry in D and Q axis, we can only model D axis, and for Q axis, we simply assume it had the same factor. Okay, so for either case, we only just need to study saturation in D axis. For cylindrical rotor generator, we assume no saturation in Q. For round rotor generator, we assume the same saturation in Q. So we only focus on estimating the K factor in D. So this is how the flux linkage change with the increase of the field current. So X is the field current. And Y is the flux linkage, which is the total flux linkage considering both D and Q axes. Okay. But because we assume it's open circuit test, so there's no terminal current, which means we can ignore Q axis flux linkage, right? From previous slides, we indicate actually the flux linkage really mainly just we can assume the zero current in the Q. Okay, so this curve will have slope almost same before saturation. So which means this curve is tangent with a straight line and stay very close with a straight line beyond a certain point, right? It will separate from that straight line. So we can use this straight line as a perfect generator without any saturation. But when the load increase, so the gap will be gradually growing. Okay, so typically we can use exponential function to model the gap between this curve and that straight line. And also from this figure, we know if we want to estimate the KSD by definition will be the inductance divided by the unsaturated inductance, which from this triangle, we can know the KSD is simply just psi AT divided by psi AT0. Psi AT0 is actually by using the same current. If without saturation, we can generate this much of flux linkage. With saturation, we can only generate psi AT. So there's a big gap. So if we divide psi AT by psi AT0, so that is exactly the factor we're looking for. And the psi AT0 will be equal to the actual flux linkage plus this gap. The gap is defined to be psi I. Okay. If you know those two currents, so the factor will be I0 divided by I. Okay. What is I0? So I is some typical, like your loading condition I, right? So by having the field current I, you can generate the air gap flux linkage psi AT. If the generator has no saturation, you don't need this current. You can reduce current to I0. That can generate the same amount of psi AT. Then I0 divided by I will be the factor you are looking for by utilizing this triangle. Okay, so there are a number of ways you can do. You can estimate the factor. First, if you know the IOAD and the IOAD without saturation, so that would be the ratio by definition. Second, if you know the actual characteristic, okay, and compare to the straight line without saturation, by knowing that this gap, that you can utilize this formula to calculate the factor. Or you can, if you know for the current with saturation, you have to have current I to generate the flux linkage. Without saturation, you can reduce current to I0. So so dividing the I0 by I, you can also get the same factor. So there are a number of ways you can estimate that factor. So next step, you just need to do some tests. There are some more detailed examples on Quinter's book, so you can read that example on how to estimate. For this course, we only just want to introduce some typical model to model saturation, which you will be able to see from some manuals of simulation software. This is one type of model. So to model this curve, split this curve into 3 mathematical functions. Okay, so they use one equation for each section. For example, so will be the open circuit characteristic. So I assume the curve can be split into the green part, red part, and blue part. So for the green part, that's purely linear curve without any saturation. The blue part is very saturated, okay, oversaturated, so that is also linear. And the middle part will change the gap from the unsaturated straight line in the exponential function. Okay, so we're going to introduce the formula for each section. Segment number 1, when the flux linkage is lower than the first threshold, psi T1, and basically the gap is 0. It's just a linear function. So when we move to the same segment number 2, it will be higher than psi T1, so it will be an exponential function. So to model this curve, we need at least 3 parameters. We need this magnitude of this constant A, and also a constant with the exponent. And also we definitely need to know exactly that boundary, where that boundary is. So we need those 3 parameters in order to model this curve. So if you want to model generator for the saturation, you need to define those 3 values. Okay. So in the blue part, that's also straight line. The straight line, you just need to know the boundary point, which is psi T2, and also you assume there's some slope. You just call it L ratio or whatever coefficient. Okay. Then you just need to utilize the point at the starting point, so you can write down this linear equation. So for all the parameters I colored in red or blue, which need to have some values, okay, in the model. So if you want to use this model, you need to look for those values. Then you can draw this function. So once you draw this function compared to the unsaturated curve, and you can calculate this ratio and multiply this ratio, multiply the unsaturated inductance by this ratio, that will give you the accurate inductance. Please note the segment 1 and 2 with this model, they are not connected, because you can plug in this point. You can calculate the value using the equation of the second segment. So you let AT in the second equation by psi T1, and you will notice that gap is not 0. It is ASAT. So in the second equation, you let psi AT to be psi T1, right? This one will be 0. And the E0 will be 1. So psi 1 will be A sat, will be factor A. But based on first equation, this psi 1 is always 0. But most of model, they just ignore that disconnection because usually A value is very small. Okay, then we can utilize the second equation, third equation, because we assume they can be connected. So they have to be, so which means if we use a point at the boundary, they need to meet both sides for the equations. So we can have those 2 equations. Then finally, for this model, we need 5 parameters. We need A, B, and the first boundary point and second boundary point, and also the slope of this line. So if you know those 5 values, you can draw this figure. Yes. All right. So, so this is the model, the same model I showed at the beginning of the lecture. That is what I call the most accurate model for the equivalent circuit. You can find this model in many software. Maybe some software, at least the Prototype Lab software, still provide this model if you know all the parameters. And what we just talked about on the saturation will be utilized to this model. So this is exactly on the manual, on TSAT manual. TSAT is actually the transient stability analysis or assessment tool manual. So they give you all the parameters, so you can tell that XAD basically is just LAD, SAQ, XL is basically just LL, because for per unit XL, X and L are the same. So you can tell it's like XKQ1, RKQ1. So basically, they follow the exactly same notation here in those two circuits. And the last part give you 5 parameters to model saturation. So those exactly match the 5 parameters we just talked about. So A, B, the first boundary, the low boundary, the middle boundary, and also the last one will be the slope. Okay. Yeah, this is the last slide. So we'll continue a little bit on the saturation on Thursday.